All right. So we've done the citric acid test. It looks like a pretty good way to cool stuff. Citric acid is nice because we can carry it as a solid, and then we can dissolve it up in the mountains. It does a pretty good job at cooling stuff. You get a delta H in the neighborhood of like, depending on how your experiment went, in the area of 40 to 50 kilojoules per mole. We will learn how to calculate a true value from accepted data on Friday, tomorrow. So we'll come back to that delta H value for the citric acid in a little bit. But before we get there, okay, there's a new problem. There seems to be quite a demand for frozen yogurt at the ice cream stand in the mountains. So ice cream is all well and good, but we could really branch out and maybe offer some frozen yogurt. To do that, though, we need to cook. We need to be able to heat a solution. So, because the way that we make frozen yogurt is we take the ingredients and we have to heat them up so that certain chemicals will react together, and then when we cool it down, it will form that frozen yogurt texture. At least that's what I'm going to pretend. So, we want to find, now we need a new reaction where we could find a delta H that is going to be negative. We want a reaction that will give off energy that we could use up in the mountains. We're not allowed to harvest trees in the woods. We don't want to truck in gasoline or propane fuel or something like that. We want a nice chemical reaction that we could potentially use. This is a problem that comes up all the time, okay? Now, we could go through and conduct a bunch of experiments. Again, like we did, we've already done a couple of experiments on determining delta H values. But there might be some other ways, easier ways, that we could go through and solve for delta H. If we used experimental data from other people, there are techniques that we can do to combine different results, different experimental data, to go through and calculate the delta H for a new reaction that we might be interested in. And in particular, one of the first ways we do that, the first way that I'm going to show you today, is by looking at whole chemical reactions. We could take the delta H for a bunch of chemical reactions and we could add them together. Let's say one of the things that we want to investigate is we want to investigate buying some heaters from some military suppliers. So if you've ever heard of an MRE, which is called a meal ready to eat, this is a commercial civilian version of these packets. This is something that the military uses. Backpackers use them as well. So you have some food stuff in here. This is mango peach with applesauce. This packet here is Cajun style rice with beans and beef sausage. Sounds pretty tasty. There is a dry roasted peanuts. There's some candies. There is a beverage base powder, orange. And there are some M&Ms. But, when you're up in the woods or if you were out, say, in the middle of Afghanistan, you might prefer to have a warm meal. So you want to take this Cajun-style rice with beans and beef sausage, and you want to heat it up. And you don't particularly want to have to start a fire or find some wood. That could produce smoke, which could potentially be very bad for your health for a variety of reasons. So the military has developed or contracted out to produce what they call an FRH, a flameless radiation heater. And this is one. This comes in the packet, okay? This is a heater. This will warm that food right up, okay? It will get it to, like 110 degrees Fahrenheit. So a nice warm dinner, like a normal warm dinner sort of temperature. Of course, it's going to depend on ambient conditions and all kinds of stuff. But the way these work fundamentally is this packet contains magnesium. Okay? It contains finely powdered magnesium. And what you do is you tear this open and you pour in some water. Okay? The magnesium reacts with water, and they have a finely powdered magnesium here, so the reaction goes fairly quickly. And during that process, it releases quite a bit of energy. This will get very warm. Okay? So the magnesium reacting with water produces magnesium hydroxide and hydrogen gas. The hydrogen gas just sort of bubbles out and escapes. It's not burned. Okay? This is we're using the chemical reaction to produce this energy. Okay? Now, what we want to do is we want to calculate how much energy is produced in this reaction. What is the delta H? How much energy per mole of magnesium reacted? Which is nice. Magnesium has a coefficient of 1. We'll solve for the delta H. That would be the value. Okay, guys? No pokey pokey. So, to do that, there are a couple of different techniques. The one we're going to use involves what we call Hess's law, developed by a chemist. And the idea here is that if we conducted a series of other experiments, or somebody else conducted them, and we saw their values, if there is a way that we can take a system of chemical equations and rearrange it so that when we add it all together, it gives us our overall equation. Then, if we add together the delta H values for the reactions that we're using, we'll have the delta H for this reaction that we're trying to find. Okay, this is what we call a state property. The state property is one where it doesn't matter how you get from the start to the end. It doesn't matter how I put together a series of equations. As long as this series of equations ends up with the same starting and ending point, the delta H values will be the same. So, let's say that we looked up these 4 equations. I gave you these 4 equations, and I said from these 4 equations, you can combine and rearrange these 4 equations to solve and get this equation here. Okay? So what we want to do is we want to look at these 4 equations, and we want to come up with a system of looking at these equations and rearrange them. I can flip them. So I could take the products and make them the reactants, flip it around, which would change the sign on the delta H. I can multiply the equations by some number. And that's it. That's basically all I can do. I can flip an equation around, which changes its sign. I can multiply an equation by some number, which we then would go ahead and multiply the delta H by. Now, the basic procedure here, the basic process that we're going to do is we're going to go and we are going to look for elements or molecules that occur in only one place. If you identify elements or molecules that only exist in or occur in one place, that is your starting point. Okay? That's really where you want to start. So for instance, the magnesium right here, these are the only 2 places I have magnesium. Occurs once in my target equation, and it only occurs once in my given set of equations. So what I want to do is I want to say, all right, this magnesium is on the right side, or it's on the correct side. It's on the left-hand side. I want it on the left-hand side.
On the sheet, it says 2 Mg plus 1/2 O2, and there it says plus O2.
This is correct. This is correct. You'll see in a sec that it is going to change. Exactly, and I think that's probably what happened. It got confused between the 2. So we have, however, in our given set of equations, this given set, this has 2 magnesium in it. And my target equation I'm trying to build only has 1 magnesium. Since there's no other magnesiums any other place by themselves as an element, I know that what I want to do is I want to take this equation and I need to multiply it by some number so that I'll get 1 magnesium. What do I need to multiply it by? I got to multiply it by 1/2. So this is going to become, from 2 magnesiums, it's going to become 1. This oxygen is going to become 1/2. And this magnesium oxide is going to become 1. So I multiplied each part of these by 1/2. Now, if I multiply the equation by some number, I have to multiply the delta H by the same number. So I'm going to take this and multiply it by 1/2. Now, I don't ever want to touch this equation again. I did this change to it so that it would match the magnesium. If I change it, it won't match, so I know I'm done messing with that equation. Now I want to say, all right, is there any other molecules that only exist in one place? So the H2O exists in a kind of a lot of places. I want to be a little careful with that. Magnesium hydroxide is probably the next best one. This magnesium hydroxide exists here in my target equation and here in my final equation. Question? Yeah, that was a typo on the sheet, so you want to correct that. We changed it, so it was 2, 1, and 2, but then we multiplied it by 1/2. So it became 1, 1/2, and 1. And I think when I tried to do that on the sheet, when I cut and pasted, it didn't work quite right. So yeah, I want magnesium hydroxide. And look, hey, it's 1 magnesium hydroxide and 1 magnesium hydroxide. Do I need to do anything to this equation? No. I want to leave it exactly where it is. Notice also that, see this MgO? That's going to cancel out MgO here. Because MgO doesn't exist in the target equation. So that's good that these two things cancel out. Now, there are some other things that we could look for. What else might we see here? Yeah, we could look at the H2. Okay, that's probably our next best one here because these waters are going to get a little tricky. Some things we're going to have to look at. But notice my target equation has H2 on the product side, and my given equation has it on the reactant side. So I need to flip it. I need to take this equation and I need to flip it around. Products became reactants, reactants became products. I have flipped it around. Do I have the right number of hydrogens? So I don't need to multiply by anything. Okay? But I did change it. I flipped it around. So what I need to do is I need to take this delta H and multiply it by -1. I need to put an extra negative sign on it. And I like to actually write an extra negative sign. I leave myself some space so I can write in the negative sign. That way I can see what I did when I'm going back and trying to figure out where my mistake was. I can see that, oh yeah, I flipped this, so I did that, that was right. Okay, oh, I multiplied that by 2, 1/2 or whatever, so I can check that. Finally, there's only one thing left in my target equation here, right? It's the waters. So now I got to make the waters work. Here's the important thing. You have to look at the phase. Phase changes involve energy changes. That's why in the lab yesterday when we put the baking soda into the water before, when I had the wrong set of instructions, it didn't work right because our target equation was for solid baking soda. So when we dissolved it, made it aqueous, that involved an energy change. Okay, so we want to make sure that we have the exact same phase information as well. So this is water as a liquid. Water as a liquid. So I need to make sure I have the right amounts of those. Notice other things start to cancel out here. Right? My oxygens canceled out. Okay. What else is going to cancel out? The magnesium oxide will cancel out. And look, water as a gas. Water as a gas. What did I do here? Magnesium oxides, we got rid of the waters. Oh yeah, see we had a water here. So I have 2 waters. Okay, so that's 2 waters. And I'm canceling out things that cancel out. Is there anything else left that I can cancel out? Nope, we took rid of the water as a gas, we got rid of the magnesium oxide, we got rid of the oxygens. All those things will cancel out. So if we add this all up, if I take all these pieces and add these things, the things on the reactant side stay on the reactant side, the things on the product side stay on the product side, I get 1 magnesium, 2 waters, a magnesium oxide, and hydrogen. So I got it right. It matches. That's good. Now what I need to do is I need to add these delta H values up. Okay, so I'm going to go ahead and add those delta H values up. 1 half of this is 602. I got negative 37. I've got positive 44. And I've got negative negative or positive 242. The delta H for this reaction is the sum of these guys. Yeah. I just stacked the two H2Os on top of each other. Remember, we had one from the magnesium hydroxide reaction and one from the H2O hydrogen plus oxygen reaction. That was why there was two. Yeah. And they remember the two didn't have to be in the same reaction. As long as the whole side contains the right number of them, we're okay. So you look for elements or molecules that only exist in one place in your target and one place in the given set of reactions. Those are your keys because you know what they have to be multiplied by, you know what side they have to be on. Once you've got all of those put in, then you can start to look at other elements, other compounds, to make sure that they cancel out, to make sure that you have the right number of them, and then they're on the right side. When you're all done, check to make sure that it adds up to give you your target reaction, then add the delta H's. 1 half. Okay? Questions about this process? This is called Hess's law. All right? H2O, H2O, just stacked on top of each other. Because I moved them up physically. I just moved them up there. All right. Your turn to practice. Here's your target equation. This is another possible reaction that we could use to heat stuff. Calcium hydroxide reacts with carbon dioxide to produce water and calcium carbonate. Okay? I want to know what is the delta H? What's the enthalpy change for this reaction? Here are 4 reactions that you should be able to find a way to add these together to give you this target reaction. Okay? Because the heat's down low. All right, let's go through and look at this. So here's what we've got. Find elements, compounds, molecules, whatever, that only occur in one spot. Okay? So I would, first thing I'd look at is this calcium hydroxide, right? I've got calcium hydroxide on the left-hand side, the reactant side. I see it, this is the only place it exists in my given set of equations, but it's on the wrong side. So I need to take this and flip it around. Okay, so I flipped it around and I put a negative, extra negative sign on here. Now, what's another thing I can key off of? Something that's in here that only occurs in one place down here. Carbon dioxide or calcium carbonate, they're both right here. Hey, they're on the right sides. I got carbon dioxide, calcium carbonate, they're on the correct sides. So what do I have to do to this equation to get the right number of them? I got to multiply that equation by 1 half, which gives me 1 calcium oxide, or carbon dioxide, half of an oxygen, and 1 calcium carbonate. And I'm going to make 1 half this number, multiply by 1 half. Now it gets a little tricky because there's not really anything left here. The water occurs in a bunch of spots. It's a little trickier to deal with. So you might, and this is what I think to myself, I say, okay, I don't want to change these equations. What parts of these equations do I need to cancel out? Well, I have half of an oxygen. I have to get that to cancel out. Half of oxygen only occurs in this third equation. But it's on they're both on the left-hand side, so I know I have to change this equation to make the oxygens cancel out. I don't need to multiply. It's 1/2 oxygen, 1/2 oxygen. I need to take this equation, I need to flip it around. Now these oxygens will cancel out. That'll be great. Okay? The last thing here I have to say is, okay, again, I don't want to change any of these three, but look, I have 2 liquid waters here. Liquid water. This is a gas, so that doesn't cancel. I need 2 liquid waters on the left-hand side to cancel out, because I shouldn't have any liquid waters in my final answer. So I can take this last equation and say, oh, I need to multiply this by 2 so that the liquid waters will cancel out. Now I go through and I double check. Everything cancels appropriately. 1 gaseous water is canceled out, leaving me 1 of them. The liquid waters cancel out. The hydrogens cancel. The oxygens cancel. I'm left with what I'm supposed to have. So I can add these values up and I can get a delta H of negative 69 kilojoules per mole. Okay? Are we okay with that? Okay. Of course. The pass just went, but so I don't have the pass. If you can wait a few, somebody just walked out the door. If you can wait, would be better. All right. She's skeptical. That's a skeptical face. Huh? So yeah, we might want to be careful with producing hydrogen gas in the wilderness. That didn't work so well in our rocket. The fire and the burning and the explosions.